Hi, in this video I'm going to continue on the topic chemical equilibrium, and in this video I will be focusing on some calculation involving the equilibrium law as well as the equilibrium constant expression. So let's get started. Now here, this is just to refresh your memory about the equilibrium constant expression. It is basically the product concentration at equilibrium divided by the reactant concentration at equilibrium. Of course, you need to pay attention to the stoichiometry of the equation. Now let's look at down here. We have a worked example. We have this reversible reaction, and we start off by adding 0.1 mole of the reactant into 100 cm cube of distilled water. At equilibrium, it is found that there are this quantity of Fe3+, which is one of the products. Now you're asked to calculate Kc and state the unit. Now you can tell, if you are going to calculate the Kc, you are going to use the equilibrium constant expression, and from there you are going to find out all the equilibrium concentration of the chemical species. You sub into this equation and then tap the calculator and find out the answers. So we need to look for all these equilibrium concentrations. Now from these given information, they are in moles and volume, so perhaps we can convert it into concentration first. Now, so the first step is we calculate the initial concentration of the reactant. So number of mole divided by volume, you get 1 mole per dm cube. And from the other information here, you can calculate the equilibrium concentration of Fe3+, again, mole over volume. Now, even though the reaction has taken place, the total volume of the mixture should remain unchanged. So it should be 100 cm cube before and after the reaction. So now you find out the equilibrium concentration of Fe3+. Now, the next step is very important. The next step is you're going to use this table, and I will call this one a RICE table, R-I-C-E. Now, R stands for reaction. It will be best if you can copy the equation once more down in this empty space. So this R stands for reaction. Now, I stands for initial. Now, initial concentration or initial number of mole. So here we use concentration, so we just sub in the initial concentration of all the chemical species. In this case, we start off with only the FeSCN2+, right? So that would be the initial concentration, and at the beginning, we should not have any Fe3+ and thiocyanate ions. Now, C stands for change. So when the reaction takes place, forward and backward reaction will take place until equilibrium is reached. Then the concentration will remain constant. So these changes basically means the change in concentration when the system is working itself towards equilibrium. Now, how do we come up with these numbers? Actually, we do not know this number at the first place. So after you put down the change here, you can leave these three numbers blank at the moment. And we move on to E, equilibrium. And this is the equilibrium concentration, and also the most important part, because remember, at the end, we are trying to find out all the equilibrium concentration and then plug it into the Kc expression. Now, so do we have any information regarding the equilibrium concentration? Yes, we do. We have the equilibrium concentration of Fe3+ being 0.03 mole per dm cube. So this is coming from here. I can highlight it for you so you know where these data come from. Okay? Now, so at equilibrium, there are 0.03 mole per dm cube of Fe3+. And from here, we also be able to deduce the equilibrium concentration of thiocyanate. This is because all the Fe3+ and SCN- is coming from the FeSCN2+. And both of them starts from 0. So if at the end we have 0.03 mole per dm cube of Fe3 plus, we may as well have the same concentration of SCN minus. So this is how we can put down 0.03 here. Now, this 0.03 coming from 0, therefore the change would definitely be plus 0.03. So this is how we put down these two numbers. Okay. Now, going back to the reagent part here, so since the mole ratio of FeSCN2 plus to the two products are all 1:1 ratio, so during the change, if Fe3 plus has increased its concentration by 0.03, then the concentration of FeSCN2 plus should also decrease by the same quantity. So therefore, minus 0.03 mole per dm cube. Now, initially 1, the change is minus 0.03, so the equilibrium concentration will be 0.97. Okay, so this is how we are able to get all this data, fill in all the boxes of this rise table. Now, like I said, this is what we are looking for, because now we got all this equilibrium concentration of the chemical species. And next step, we need to devise our equilibrium constant expression. Okay, product over reactant, sub in those numbers, tap the calculator, you get the answer. Okay, make sure the units, you follow the Kc expression, 2 concentration divided by 1, so it will be mole per dm cube. Okay, so this is how it works. Remember the steps. First step, make sure all the information given are converted into concentration. Secondly, devise the rise table, sub in all the information that you can get, and finally find out all the equilibrium concentration. Third step, put down the Kc expression. In public exam, this expression may give you 1 mark. So even though you can't work out the rise table, you put down the Kc expression. Okay, and then you plug in the number, tap the calculator, and get the answer. Make sure you get the units correct. Okay, so this is how it works. Now, let's go to the practice question. Now, I'm going to demonstrate to you the first one, and then I'll give you some time to work on the second one, as well as another question from the later pages. So, this one. Now, let's first of all read the question. We have the triiodide ion, which is this I3 minus, as shown here. And then it dissociates in water to give iodine and iodide, as shown in the equation here, reversible reaction. So we start by adding 0.1 mole of ammonium triiodide into 1 dm cube distilled water, and the value of Kc, this time it is given, they give you the Kc. Now if they ask you to calculate the equilibrium concentration of iodine ion, they are looking for I minus at EQM. Alright, so it's a little bit different than the worked example, but the methodology is very similar. Now, so what will be the first step? The first step is, of course, to convert the data into concentration. So first of all, we have the triiodide ion, okay, initial concentration, which is equal to mole over volume. Actually, it is the same as the number of mole since it is in 1 dm cube. Okay. Now, no more concentration we need to work on. Let's put up the rise table. So RICE. Okay. Now reaction, again we will copy it one more time. Doesn't matter. Okay. So we are able to have the triiodide ion concentration in the beginning, 0.10. We don't have any iodine, we don't have any iodine. Okay. Now, changes, equilibrium. We don't have these numbers, we don't have these data, so what are we going to do? Now what are we going to do is, we want to devise a letter to represent the change. So in this case, I will use perhaps Y as an example. Now from here you can tell, the reaction should proceed in a way such that part of the reactant will be consumed to form product, because you don't have any product, no backward reaction can occur. So I was expecting some I3 minus will be consumed Okay, so I will put down minus y. Okay, now if it is minus y here, what should be the change in concentration in terms of y? Here must be plus y, right? Think about it. If it has 0.01 mole per dm cube of iodine being consumed, then it should also increase the concentration of both products each by 0.01 mole per dm cube, isn't it? So this is how it works. And then you just put down the equilibrium concentration in terms of y. Okay, just like this. Now, with all this equilibrium concentration, we will plug it into the Kc expression. So Kc equals to I2 minus EQM, I minus EQM over I3 minus EQM, isn't it? Okay, then you just plug in the number, you realize that it is, okay, y squared divided by 0.10 minus y. Okay, and this one we know the value, which is 2.0 times 10 to the power negative 4. Okay, now at this moment you can simply solve this quadratic equation. Now at this point you can use two different methods to work on from this point. You can use the quadratic method. So let me show you. You can use the quadratic method. You can expand the bracket here first of all. So you can have like multiply both sides by the denominator. You get y squared equals to 2 times 10 to the power negative 5 minus 2 times 10 to the power negative 4 y, isn't it? Rearranging the term, you got y squared plus 2 times 10 to the power negative 4y minus 2 times 10 to the power negative 5 equals to 0. Then you can solve this quadratic equation. Okay. A is 1, B is 2 times 10 to the power negative 4, C is minus 2 times 10 to the power negative 5. So you can see y equals to this number, or the negative 1, okay? But it's not mathematics, so you can simply put down the valent roots of the equation, okay? So this is how you get y, right? Now another method that you can use, we can also compare the two methods. So here, this is method number 1, there is method number 2. Method number 2 is that we will put down since, okay, Kc is small, okay, because this is like 2 times 10 to the power negative 4 is quite a small number. So Kc is small. Therefore, 0.10 minus y, okay, is more or less equal to 0.10. We can take this assumption. Okay? You may say, how is it related? Now think about it. Do you remember the magnitude of Kc? When Kc is very, very small. We look at this Kc expression again. When Kc is very, very small, that means you have very little product and a lot of reactant, right? In other words, the reactant does not react much. Okay, the forward reaction hardly proceed. Okay, so this negative y here, if the reaction hardly proceed, you should expect to see a very tiny change in concentration of triiodide ion. So the y will be very, very small, right? Now you have 0.1 minus y, which is a very, very small number. It's just like 0.1 minus 0.000000001 is basically the same, right? It's basically no change. So this is how we can do the assumption. Now, after we do the assumption, then the equation will be much simplified. Now, we will have y squared over 0.1 minus y equals to 0.1. So 0.1 over here equals to 2 times 10 to the power negative 4. Then you can easily type your calculator for this equation. You can have square root 2 times 10 to the power negative 5. And you register this one. Okay? Now, so you can compare. Actually, these two numbers are very close to one another. Okay? Just differ from each other by 0.1 times 10 to the power negative 3. Okay? Now, this is the second method. In this case, it is also acceptable. Okay? Now, so choose yourself. You can go for a quadratic equation of which you can get a more accurate answer, or you can take the assumption. But bear in mind, when you take the assumption, the Kc must be small. So this one is regarded as small, then you can do the assumption. But if Kc is relatively large, then you can't do this assumption, and you must resort to quadratic equation. And in DSC, they require you to know how to perform quadratic calculations. Okay? Now, after calculating the y, actually what is y? Y, you can come back to the equation over here. You see, y is basically the equilibrium concentration of iodine. Okay? So the equilibrium concentration of iodine would be this one. Okay? Of course, you give them back the units. Okay? Mole per dm cube. Okay? So this is how it works. Okay? Now, so far I have shown you two examples. Now it should be your time to work on some questions. So down here, spend some time work on this question, and then you pause the video. After you finish it, resume the video and check the answers. All right, let's have a look. Carbonic acid, weak acid, dissociate partially in water to give carbonic ion, hydrogen ions, as shown in the equation here. It starts with 0.2 mole of carbonic acid, add into 500 cm cube of distilled water, and at equilibrium there are this quantity of carbonic ions. Calculate Kc and state the unit. So this question is essentially the same as the one on the left, isn't it? So we should start by converting the information into concentrations. So we can have carbonic acid. Initially, concentration, it should be 0.200 divided by 500 divided by 1000. And this should give you 0.400 mole per dm cube. Okay? Right. Okay, and then at equilibrium, so the carbonic ion CO3 minus at equilibrium, this one is 5.92 times 10 to the power negative 7. Again, converted into concentration, so 500 divided by 1000. This one equals to okay, 1.184 times 10 to the power negative 6 mole per dm cube. Okay? Now, next step is to construct the rise table, isn't it? The rise table. So, copy the equation down as the R. So, H2CO3 becomes CO3, 2 minus, and 2, H plus. Okay? The initial concentration here is 0.400. We don't have any carbonate. Now H plus, even though in pure water we have some H plus, but the quantity is so small that we can neglect it. Okay, so we just assume that it is 0. All right. Now, again, changes. We'll let it empty at the moment. We look at the E. because you know the equilibrium concentration of carbonate being 1.184 times 10 to the power negative 6, isn't it? Now, from here, we can also calculate the equilibrium concentration of H+, because all of these products are coming from the reactant. Okay, so this one should be double of carbonate ion, right? Should be double of carbonate ion. So answer times 2, we register 2 times 2.368 times 10 to the power negative 6. Okay? Then the change would be plus 1.184 times 10 to the power negative 6. Here, plus 2 times 2.368 times 10 to the power negative 6, right? And over here, since this one and this one is 1-to-1 ratio, so if we plus 1.184, it should minus 1.184 as well. Okay? Then you tap the calculator. 0.4 minus this one, you get, wow, 0.399998816. What a huge number. Okay? Now, then the last step is simple. You just do Kc. Kc equals to CO32 minus EQM, H plus EQM, remember square over here, divided by the concentration of carbonic acid. Okay, I'm not going to write it down. I simply tap the calculator myself. We have 1.184 times 10 to the power negative 6 multiplied by 2.368 times 10 to the power negative 6, close bracket, square. Okay, and then enter, divided by 0.399998816. Okay, so the answer will be 1.66 times 10 to the power negative 17. Okay, and the unit here would be mole square dm to the power negative 6. Okay? So that's the answer. Okay, now I want you to do one more practice. So can you turn to page 19. Page 19. Can you please turn to page 19? Okay, so I want you to also work on this question 3 here. Okay, you can pause the video, spend some time on it, and resume the video and check the answers. Alright, we have this one is an esterification reaction. Kc given is being 4. In this experiment, 2 mole of ester and 2 mole of water are mixed. Calculate the number of mole of each chemical species when the equilibrium is reached. Now, in this case, they give you the concentration, or they give you the mole of the product. Okay, so you do rise table, right? You may ask, hey, sir, what about the volume? We don't have the total volume here. Now, actually, it doesn't matter. In this case, I will tell you why later. This case, we can stick with mole. We can use number of mole to represent the concentration. Okay, so let's do the rise table. So copy the equation down. Ester and also water. Okay, so we start off with no acid and alcohol, but we have like 2 moles of ester and 2 moles of water. Okay, now the concentration, the changes, so we do plus y over here, minus y over here. Okay, because you can tell the reaction should go from right to the left initially. Okay, so at the end, this one should be y, 2 minus y, 2 minus y. Okay, And all we have to do is to solve y, then we have all these numbers, right? So Kc equals to the ester EQM multiplied by water. Now remember, water is not a solvent. Water is one of the reagents in this particular example. Because we will actually add pure reagent inside, not a solution form. Then basically you get 2 minus y over y squared, okay, like this. So this one equals to 4, and then you can solve the equation. .667 or -2. It's not going to be -2, right? So y is 0.667. Okay. Now, so basically, you are able to find out all the number of mole of each chemical species. This one would be 0.667, 0.667. This one 2 minus 0.667 should give you 1.33, 1.33. Okay. So this is how it works. Now, B here is something I want you to pay attention to. It's a little bit challenging. Now, to this equilibrium mixture, so we already have this equilibrium mixture. How many moles of ethanol must be added in order to increase the number of mole of ester by 0.1? Okay, we want to add certain quantity of ethanol so that at the end we want to have 0.1 mole extra ester. Okay. Now, question like this, we still use the rise table to help us to rise table. Now, the key about equilibrium constant calculation is whether or not you are able to set up the rise table correctly. Okay. Now, pay attention. This time, we have an equilibrium mixture, and then we add something into it. So the initial concentration of all the chemical species should be the equilibrium mixture. So we start off with 0.667, 0.667, and then 1.33, 1.33. Okay. Now, so this is the equilibrium concentration. Now, we add something so that the equilibrium will change. Now, at this moment, if all these chemical species are at such concentration, there is no change, right? They are in equilibrium, right? In order to bring about a change of the concentration, we need to add something into it. And according to the equation, we add some ethanol, okay? And how many ethanol, how much ethanol? No idea. So let's just give them, let's just say it adds, okay, maybe X, it adds X, okay? Add X, right? Now, when they add in X to it, then there will be some change, right? There will be some change, and you can tell part of the reactant will be consumed, forming the product. So at the end, you want to have more product, okay? Especially for ester, because we are looking for 0.1 mole extra. So here, we should have plus 0.10, isn't it? Okay, we want to increase the number of mole of ester by 0.1. So at equilibrium, we should expect to find 1.43 mole of ester. Okay. Now, if it increased by 0.1, water should also increase by 0.1, because again, these two are coming from the reactant. So if it can increase by 0.1, it will also increase by 0.1, 1-to-1 ratio. So this one is also 1.33. Okay. Now, therefore, this one should be minus 0.10 based on here, minus 0.10 based on, again, here. So, At equilibrium, this one you should have 0.567. This one you should have 0.567 plus x. Okay? Now, with all this equilibrium concentration, we can plug it into our Kc expression again. Remember, the Kc is constant as long as temperature is constant. Changing concentration does not affect the Kc. Kc is always 4 in this case. So, we plug it into the equation. So, Kc equals to 1.43 square divided by 0.567 times 0.567 plus x, which is equal to 4. Okay? Then you can simply solve this equation. It's quite tedious to solve this. We can solve the new numbers first. We can do like you have this answer divided by 4, you get 0.335. Okay, so you need to add 0.335 moles of ethanol in order to get 0.1 mole extra ester. Okay, so that's the idea. You can always double check. You can have like
1.43. Okay, we just want to sub in all these numbers into the Kc expression again to see if we get 4. We can have this one divided by, down here, 0.567 multiplied by 0.567 plus 0.335.
Yeah, we got a number very, very close to 4. So that must be correct. Okay? So, that's it for this video.